In this lecture, we're going to do a short review of complex numbers, functions of complex numbers, and complex variables. So most of this should be reviewed from your previous math classes. But in general, we can define a complex number in rectangular form as, say, the variable z, which is equal to some real part, x, plus the imaginary number I times the complex part, where I is equal to the square root of minus 1, as we know. And for this class, we're going to refer to that as j as well. And this comes from history that I is current, and so in the complex analysis of related to control theory, a lot of times we'll replace I with j. So in other words, we can write z is equal to x plus j y. We can define plot this in the S-plane, or what we also call the complex plane. And that is to say, we could draw a set of axes that had the real part along the horizontal axis and the imaginary along the vertical axis, and we could plot a vector, or what's also known as a phasor, out to the point that has x and y for coordinates, and this would be the phasor z, which is equal to x plus j y. That's an equal sign. And we could also notice that we could draw kind of the complement, or what is really the conjugate of that, the conjugate, which is, we know, to take the negative of the imaginary part. We can also define an angle theta, which is measured from the x-axis in the counterclockwise direction, and a distance r, which is the length of the vector or phasor out to the point z. In this case, then, we can look at this and say that x is just the distance r times the cosine of theta, and y is the distance r times the sine of theta, where r is obviously just using standard Pythagorean theorem, the square root of x squared plus y squared. And using this relationship over there, we can see that theta is just the inverse tangent of y over x. Using these ideas, we could also write this all down in another form. We could say z, again, just make a substitution x and y into, for z up here, r times cosine theta plus j times r sine theta. And that's just going to be r times cosine theta plus j sine theta. And we can use Euler's formula. And Euler showed that this expression here, cosine theta plus j sine theta, is just e to the j theta. And so that means we can write z as r e to the j theta. And this is known as polar form, right? Because it's really a polar coordinate system. R is the distance, theta is the angle there. Sometimes this is written as r angle theta, but depends on how you want to write it. One thing to notice, just looking at polar form here, is that the conjugate of z, so if I look at z star, that's going to be x minus jy, when again, if we go back and use this trigonometric relationship for x, r, and theta, that's just r times cosine theta minus j sine theta. And since the sine of minus theta is equal to minus sine of theta, and cosine of minus theta is equal to cosine of theta, then we can write down that the conjugate of a complex number is just r times e to the minus j theta. Finally, one valuable aspect of the conjugate is that if we take z times z conjugate, that's going to be, however you want to look at it, I could write r e to the minus j, plus j theta, that's z, times r e to the minus j theta, which is just going to be r squared times e to the j theta minus j theta, which of course that's just 0, so that whole term is 1, so that's just r squared. Notice that's equal to the norm of, well, let me write it this way, that's x squared plus y squared, right, back from that relationship up here, which is the Euclidean norm of the phasor. So we could write that squared. So that's the norm of z squared. All right, just some various properties of complex numbers. We also can look at numbers in the terms of look at complex numbers in the sense of them being a variable. And so, for example, we can say S1 equal to sigma 1 plus j omega 1 is a representation of the complex variable s equals sigma plus j omega at some s equals s1. So, in other words, you can think of a parametric relationship for the complex variable s, and the parameters are sigma and omega here, or x and y in the way we had. We're going to use sigma and omega moving forward because those correspond to some other properties we're going to look at. But in other words, I can write s is a function of sigma and omega. So we can vary sigma and omega to vary s. And so this creates the notion of a trajectory through the s-plane, or remember the complex plane. Should be an e there. I think I left the e off the other one. So in other words, I could write down, I could draw the real part versus the imaginary part, and I could imagine that I'm at some point s1 equal to sigma 1 plus j omega 1, and then this might move along, say out to s2, which is equal to sigma 2 plus j omega 2. Now, what the variable is that causes sigma and omega to vary over time is something that we're gonna look into. Finally, another way of looking at complex variables is to think of functions of a complex variable, which is essentially what we were looking at, only now instead of using sigma and omega as a parametric relationship, we're going to use s. So in other words, I could say, well, let's let the function g of s equal the real part of g of s plus j times the imaginary part of g of s. Right? So as an example, let's say that g of s is equal to 1 over s times s plus 1. This looks kind of like the DC motor model with k equal tau equal 1. But, you know, it's just some function in general. I could have an s up here, it could be s squared, you know, whatever. We're going to look mostly, again, at rational polynomials in s, but we'll see that today in class. So, in other words, what I can imagine is that there's some s-plane out here, and I would have sigma versus omega, and I could imagine that there's some point here, s1, which is defined by sigma 1 and omega 1, and that gets mapped through the function g of s into some other complex domain, because this is a complex function. So this would be the GS plane, and there would be some phasor which is G evaluated at S1. All right, and it would have for its axes the real part of G of S versus the imaginary part of G of S, and this would be defined as the real part of G of S there, and it would have a Y component as the imaginary part of G of S. So another important definition that we want to refer to is what we call an analytic function. And complex functions, or functions of a complex variable, can be analytic or not. Or we can exclude the regions from the space which would make them not analytic. So in general, an analytic function is a function, G of S, so that's something we've defined up here, of the complex variable S. There you go. And this function is called an analytic function if in a region of the S-plane, so some region over here, if the function and all its derivatives exist in the region. And so as an example, we could see that, say, G of S equal S plus 2, that is analytic. All right. A function, say, that was G of S equal to 1 over S plus 1 is analytic only if we exclude the point S equals minus 1. All right, and so we could draw that, right, as the space sigma and omega, and then we could just put a hole here at minus 1. Okay. And then that hole essentially represents the point we're not going to include, but we would include every other point in the space. This is important down the road when we start talking about transfer functions. But in general, all this about complex variables and complex functions is important because we're going to start working in the complex domain, and these real part and imaginary part are going to have specific meaning that we'll be interested in looking at. And we just need to be comfortable with the fact that we could have a function of a complex number, and then that complex number is, of course, defined as we would define a complex variable. So S is really a function of some two parameters, sigma and omega, and the variable S is, we can characterize it and look at it and analyze it from the point of view of the geometry that it defines.